As we have seen in appearance matching, one of the key challenges is that we are dealing with very large image sets of possibly very large number of objects. And somehow we want to take these image sets and compactly represent them. In order to do that, we need to go from the high dimensions in which these image sets reside to much lower dimensions where they can be compactly represented. This process is called dimensionality reduction, and the method that we're going to use to achieve dimensionality reduction is principal component analysis, PCA. PCA, I should mention, is very widely used in pretty much all disciplines of science and engineering. So here's the problem that we're trying to tackle. We have an input image here. We have our object image set. This is a very simple setting where we basically are comparing this input image with the image set of just one object. And as we described before, the naive way would be to simply apply template matching with all of these different images to find the best match. Simply not practical for any reasonably sized object recognition system. So what we really want to do here is to transform all of these images, the input image as well as our images in the database, into a different space, into a different domain, where matching one image with another image becomes much more efficient. So first, let's talk about the representation of a single image as a vector. So here is an image that's given to you, and let's say it has p rows and q columns, so it has n pixels, where n is equal to p times q. One way that you can represent this image as a vector is by simply taking each one of the columns of this image. Say the first column is this one right here. We just write that out, and then we stack all the other columns beneath it, one after the other, and you get a single vector, which is an n by 1 vector. So this is the way that you would represent a two-dimensional image as a feature vector, n by 1 feature vector, which is in along one dimension, which is the pixel index, so to speak. Now, this mapping of an image to a vector can be done in many different ways. For instance, the way you scan the image can change. We have taken columns and stacked them up. You could take rows and stack them up. Or you can raster scan the image. Or you can even randomly sample the image. The only requirement is that whatever this mapping is from the image to the vector, you have to do it the same way for all images during learning as well as during recognition. If you do that, the results are going to be exactly the same. So anyway, we come up with a feature, we'll call that F1. And there is a way to look at this feature. This feature can be viewed as a point in n-dimensional space. What does that mean? So here is your feature on the left-hand side. It's an n by 1 feature, and you can construct a space, an n-dimensional space, where each one of the dimensions of the space corresponds to the brightness at that corresponding pixel. So this vector right here, I1, is a unit vector, and that unit vector is used to represent the brightness in pixel number 1, then you have pixel number 2, and so on, all the way to IN right here. This is your n-dimensional space. So in this n-dimensional space, where the dimensionality equals to the number of pixels, your image as a vector right here is simply a point, f prime. And this is what we refer to as an orthonormal basis. Orthonormal because each one of these dimensions is represented by a unit vector, these i's that we're talking about, and these unit vectors are orthogonal to each other. So for example, if you look at I2, I2 is a unit vector which has a 1 in the second position because it corresponds to the second pixel and 0 everywhere else. So an image as a point in n-dimensional space. And now this also gives you a sort of a slightly different perspective on template matching, which we've discussed before. So what is template matching? In the case of template matching, the way we've described it before, you have two images, I1 and I2, and template matching is done by finding the correlation between these two images. And the way that you find the correlation between these two images is by finding the sum of squared difference between the brightnesses at the pixels of the images. So you have I1 minus I2 squared over all the the difference between the two squared summed over all the pixels P and Q. P and Q are the indices for the pixels. So that's the definition of correlation. Well, another way to look at correlation now is, now that we have each image as a point in our n-dimensional space, it exactly equals to the L2 distance between these 2 points in n-dimensional space. So it's f1 prime minus f2 prime and squared. That's equal to d squared. That's the L2 distance, the square of the distance right there. And that's exactly equal to the SSD. So now let's come back to a problem of dimensionality reduction. So here let's consider a distribution of points in 3-dimensional space, just as an example. And so that's what you're seeing right here. 3 dimensions are x, y, and z. And let's say that this particular distribution of points actually lies exactly on a 2-dimensional plane within this 3-dimensional space. So that's the plane that's being shown right here. So now what that means is that it is redundant to represent each one of these points using 3 coordinates x, y, z. If they happen to lie on a plane, you can actually erect a coordinate system that represents the plane, and that's given by these 2 unit vectors E1 and E2 orthogonal to each other. That's a new coordinate system. Of course, these vectors are described in the 3-dimensional coordinate frame, but once you've done that, you only need 2 parameters or 2 coordinates to represent each point because they lie on that plane. So if we use a new 2D coordinate system, E1, E2, that lies on the plane of the distribution, each point can be represented with just 2 coordinates. That's a simple example of dimensionality reduction where we've gone from 3 to 2. So let's come back to our problem. We have an object image set, and let's say that the number of pixels in each image is n, but the number of images is m. So in your n-dimensional space, you have this distribution of points. This we'll call an appearance distribution. And the key thing to observe here is that because of the similarity between these images, the correlation between these images, the distribution of feature points in this n-dimensional space can be safely assumed to be highly structured. And as a result of that, it also resides in a much smaller number of dimensions than the full dimensionality of the space, which is n. This is the key observation that we want to exploit. So let's now talk about dimensionality reduction and principal component analysis. So now let's say that we have a distribution in n-dimensional space, but we can somehow estimate a subspace which resides within this n-dimensional space. And let's say that this lower dimensional space is given by k vectors, all orthogonal to each other. So it's an orthonormal basis. So you have E1 through Ek, where k, let's assume, is less than n, and hopefully much lesser than n. So you have this k-dimensional space. And the claim that we are making here is that it's possible to, because of the structured nature and the correlation between these images, it's possible to represent all of these points, this distribution, in this lower dimensional space more compactly, more efficiently, with a high level of accuracy. So then the real question is, what are the dimensions of this space? If you're able to compute I1, E1 through Ek, that would form an orthonormal basis. And so the problem we are faced with is, how do we compute this orthonormal basis? So that's the relationship. That's exactly what principal components does for you. So here's the first thing that we're going to do. We're going to find the mean image of this distribution. So the images that are given to us are f1 prime through fm prime. We simply compute the mean, which is this blue dot that's here. And we're going to subtract the mean from each one of these original images. So you get fm is equal to f prime m minus c. What this really is doing is changing the origin of your coordinate frame. It's moving the coordinate frame to the mean so that the distribution, all the action and the variability in the distribution is now around the origin. And so that's basically what it does. You see that we're moving the origin of the coordinate frame, our n-dimensional space, to the mean itself. Very simple. So now we can look at the structure a little bit more easily. And let's talk about the first principal component. The first principal component, which is shown by this vector right here, E1, is simply the direction. It represents the direction along which you have maximum variance in this distribution. In other words, if you take all the points in this distribution and you project it onto that direction, you just look at how it varies along that direction, that variance is going to be maximum. There's no other vector in n-dimensional space for which the variance is larger. That's what E1 really means, and that's your first principal component. It turns out that for the first principal component, really the direction of that vector E1, which is a unit vector, is aligned with the direction of a line, the best fit line you would get for this distribution. So if you apply least squares fit and you find a line, the direction of that line is the same as the direction of this first principal component. Okay, so that's your first principal component. And what does that buy you? Well, in principle, you can represent each one of these points in our distribution with now a single number, which is simply the projection of the image. We're going to use image and vector interchangeably when we talk about these points. So you simply take that image f and you project it to the unit vector E1. And what does projection mean? You're simply finding the dot product of f with E1. And that gives you a single number p. And that now becomes a representation of that image with a single number p. So every image is now represented as a single number. That's what the first principal component gives you. And you are actually representing it with a number that has some meaning to it. It is along the direction of maximum variance. Okay, very clearly, a single number is not going to be good enough for most applications. So now we can talk about the second principal component. So the second principal component has to be perpendicular, orthogonal to the first principal component, because we are trying to look for an orthonormal basis. So it's orthogonal to it. Now, if you consider E1, there's an infinite set of vectors that are perpendicular to E1. We're going to try to find the vector E2, along which the variance of the distribution is maximum. And that gives you the direction along which you have the second maximum variance in the image set. So that's E2, which is perpendicular to E1. And now you have a more descriptive representation of each image. You simply take the image and you project it onto both these dimensions, E1 and E2, principal components. How do you do that? You find the dot product with E1, dot product of E2. You get now a vector with two elements, two coordinates, P1 and P2. And so this point P, two-dimensional point, now becomes the representation of each image. And you keep going. You take the next principal component and the next one, and let's say you go all the way down to K principal components. And we'll talk about the significance of K, that is, when do you stop doing this? What is the dimensionality of the space that we are going to be able to use in an effective way, which is accurate enough as a representation? We'll get to that later, but let's say there exists some K. So this then, again, allows you to represent the image a little bit more richly in this time. In this case, you have the point F, and you're going to project the point F onto each one of these dimensions, E1 through EK, the principal components, and you get a point which is K-dimensional now, P1 through PK. So an image is represented as with k numbers where k is much smaller, hopefully, than n. That's the key idea here, which is what gives us the dimensionality reduction. So what is this equation right here? We will call this the forward projection of an image. You have an image, you've somehow magically computed your principal components, so you have this lower dimensional, k-dimensional space. You can take each image, project it to that space, and that gives you a point P. That's the forward projection. But there's also the backward projection, which is given a point P, you can reconstruct an image using that. So that's the backward projection. And the reconstruction simply means that you take your principal components and you weight them and add them together. And the weighting is done by the coordinates of P, P1 through Pk, and that gives you an approximation to the original image F. It's not going to be exactly equal because when you go from a high dimensional space to a low dimensional space, you're going to invariably lose some information, but it gives you an approximation of that image. So it is this set of principal components, E1 through Ek, that we want to find. If we find it, if you're able to find it, and that's what principal component analysis allows us to do, then that is an orthonormal basis, also referred to as a linear subspace. So basically, it's a vector space that is a subset of the larger vector space, the n-dimensional vector space, but it's also referred to as a linear subspace. And our goal is to then represent all our images of the object in this linear subspace.